All right, everybody, welcome back. Let's continue to talk about the normal distribution. The primary reason we're looking at these normal distributions in such detail is because we're going to be able to use them to answer questions about our data. Specifically, we're going to be able to figure out how common or how rare our data is. So in other words, we're going to be able to determine how likely it is to find our data just due to chance. In other words, how likely is it to find our data just due to sampling error? So that's where we're headed. That's where we're moving. Today we're going to focus specifically on the standard normal distribution. So it is a normal distribution that has been standardized. We're going to learn how to compute a standard score, and specifically a standard score that we call a z-score. And you'll see we can transform a distribution of raw scores, like for example, intelligence scores. We can transform that entire distribution to z-scores, and then we will have a standardized distribution. That's what the standard normal distribution is all about. So the question is, why would we want to standardize these scores? Well, when we have standardized scores, it's really easy to interpret those scores. So that's a good thing. Why is it easy to interpret a standardized score? Once we know a particular z-score, we know exactly where it stands in a distribution. We can pinpoint its relative standing among all the other scores. You'll see that in just a minute. And the reason why that's important is because once we can locate exactly where a score is in the distribution, we can easily compute its probability using this really handy z-table. So in the past, I told you that I was going to teach you some tricks for very easily computing probability. This is the trick. We can take our data, no matter what it is. Let's just assume right now that we're dealing with IQ scores. We can transform those scores into z-scores, which is incredibly easy to do. You'll see right here, it's a very simple formula. And then once we know that IQ scores z-score, we can just use the z-table to look up the area in the distribution associated with that score, and that value will tell us the probability of scoring in that range. So we're going to learn that procedure. You'll see it's pretty straightforward. We just need a little bit of practice. Let's continue to use IQ scores as our example, because most people are familiar with them. IQ scores form a normal distribution with a population mean of 100 and a standard deviation of 16. But as I mentioned, we can standardize the entire distribution. And when we do that, when we convert that entire distribution to a z-distribution, a distribution of z-scores, standard scores, the new mean of that distribution will be 0, and the new standard deviation will be 1. That's what happens when we standardize any distribution of raw scores. We're just using IQ scores in this example. Regardless of what it is that we measure, once we standardize that distribution, the mean will be 0, the standard deviation will be 1. We can convert any raw IQ score, like an IQ score of 100 or an IQ score of 110, or 140, or 85, any IQ score. We can take any IQ score and run it through this formula right here to transform it into a z-score. Just take a look at that formula and you'll see what it's doing. We're going to take an IQ score, that's x, subtract its mean, which we know is 100, and divide by its standard deviation, which we know is 16. So you can see here, we're essentially counting in standard deviation units, because we're going to figure out how far is that raw IQ score from the mean. Remember, we call those deviation scores. How much does that raw IQ score deviate from the mean in terms of standard deviation units? So z is going to tell us, this is the key thing, z is going to tell us how many standard deviations is that raw IQ score above or below the mean. Take a look down here and you'll see some examples that are already computed. So here's a normal distribution. Right there in the middle, we're looking at IQ scores. Right there in the middle is an IQ score of 100. That's the mean value. That's the average score. So how many standard deviations is an IQ of 100 above or below the mean? An IQ score of 100 is right there in the middle, right at the mean. It is 0 standard deviations above or below the mean. So if we were to transform an IQ score of 100 into a z-score, it would transform into a z-score of 0. And 0 just represents that that score of 100 is 0 standard deviations above or below the mean. Do you see how it pinpoints exactly where that score is in the distribution? It tells us that point is exactly in the middle. Look at an IQ score of 116. How many standard deviations is 116 from the mean? Well, that's what z would tell us. So we would take that score of 116, we would subtract the population mean of 100, so it's 16 points away from the mean, and then divide by the standard deviation, which is 16. So we would end up with a z-score of 1. That's what you see right here. So again, it pinpoints exactly where it is in the distribution. A raw IQ score of 116 is 1 standard deviation above the mean. The z-score is positive, so it's showing us that score of 116 is 1 standard deviation above the mean. So at this point, we know exactly where it's located. And the way that that's going to be helpful is then we can compute the area associated with that score. And we can figure out how likely it is to find that score just by chance. That little trick will come in the next video. Let's just go through one more example from this graphic, and then we'll start computing things by hand. So look at a score of 84. An IQ score of 84 is clearly below the mean, so it should be associated with a negative z-score. So again, we would just force it into this formula. 84 is the x value, that is our raw score. We would take 84, we would subtract 100, which is the population mean. That deviation score would equal negative 16, and then we would divide by the standard deviation, which we know is 16. So we'd have negative 16 over 16, which would equal negative 1. So that would be teaching us that a raw IQ score of 84 is exactly 1 standard deviation below the mean. So it pinpoints exactly where it is in the distribution. And then eventually we'll be able to answer this type of question. What's the probability of randomly selecting someone who has an IQ score of 84 or less? That's just one example of the type of question we can answer using these procedures. I mentioned that we can figure out these areas much more specifically using what we call a z-table. So let's look at that table and let's go through some examples. This is the z-table. It's more formally called the standard normal table, but we'll just call it the z-table for short. The table begins with the column of z values, and then it'll show us areas. So the first column shows us how much area is there from the mean, which we know is right in the middle, to a particular z-score. There's another column that shows us how much area is there in the larger portion of the distribution. We will call that the body of the distribution. So do you see, like, once we have some z-score, this might be like an IQ score of 116. It's clearly above the mean. It's to the right of the midpoint. Do you see that when we split the distribution right at that point, we're left with a larger half and a smaller half, a larger portion and a smaller portion? It's this column that refers to that larger portion. I will often call that the body of the distribution. The body of the distribution is that larger portion. That smaller portion in this table is simply referred to as the smaller portion. And you can see right here there's a column labeled smaller portion. I will often refer to that smaller portion as the tail of the distribution. So just look at the first line. You can see where a z-score equals 0. That means that is a raw score that is 0 standard deviations above or below the mean. What that means is it's right there at the middle, right at the mean. It says how much area is there from the mean to the z-score? No area, because you're right there at the mean. How much area is there in the larger portion? How much area is there in the smaller portion? Both of those say 0.5 or 50%. So what it's telling us is if you split this distribution right at the middle, you have 50% of the distribution on the left side and 50% of the distribution on the right side. That's the only situation in which those two areas, those two portions, are equal. In every other situation, there will be a larger portion and a smaller portion. Let's just look up a z-value of 1 real quickly. we know that a z-value of 1 would be equivalent to an IQ score that is 1 standard deviation above the mean. And we know that the mean IQ score is 100, the standard deviation is 16. So an IQ score that is 1 standard deviation above the mean is an IQ score of 116. So what that's telling us is that an IQ score of 116 would be right about here in this distribution. We've got a smaller portion and a larger portion that we could look up. So I can start answering basic questions like this. I can say to myself, what proportion of the population has an IQ score of 116 or less? Area equals probability. If I figure out the area in that larger portion, I can answer that question. So all I would need to do is look up that z-score of 1, find the column that says larger portion, that's the area in the body, and right there it says 0.8413. Because what that's telling me is 84.13% of the distribution is in this area right here, associated with a z-score of 1. That's how we're going to use this table. So it's going to be an incredibly useful table to us. We can very easily compute area, which means we can very easily compute probabilities, and we don't need to do any fancy mathematics. That z formula is really straightforward. We've been talking about examples having to do with IQ scores, but we can measure anything, because anything we measure, we can transform into a z-score. Anything we measure, we can transform into a standard score. And once we transform it into a standard score, we can use this table right here. That is the beauty of these z-scores. Let's answer some of these questions down here based on this graphic that we see to the left. All of the areas that we see in that graphic have been written in based on values that we find in the table. So again, let's just use this graphic right here to answer some of these questions. And then we'll get more experience looking at that table as we move on. One thing that we can learn from the table and from these graphics would be percentile ranks, or percentiles. So for example, this first question is asking us, z equals 0, which we know is right there at the mean, is at what percentile rank? Well, we don't even need to look at a graphic or a table to answer that question. We know with a normal distribution, a z-score of 0 is right there in the middle. It's right at the mean. It splits the distribution in two, so it should be the 50th percentile. And let's just verify that based on what we see. Here is a z-score of 0. We want to figure out what proportion of the scores are at that value or less. Isn't that what percentiles tell us? What proportion of the scores are at that value, a z-score of 0, or less? So I'm looking to the left of the distribution. And on this graphic, it's labeled as this area right here to the left of a z-score of 0 is 50%. So that must be the 50th percentile. Let's look at the next question. What percentage of scores have a z-value of 1 or less? So what we need to do is identify where in the distribution is the z-score that we're interested in. Here's a z-score of 1. All the positive z-scores are to the right, all the negative z-scores are to the left. So we find that z-score of 1. What percentage of scores have a z-value of 1 or less? Do you see when we're talking about scores 1 or less, we're talking about this large area in here? So that's the larger portion, what I like to call the body of the distribution. Well, we can just kind of use these numbers that we see right here to easily put together our answer. If this section right here is 50% of the distribution, and this little section right here is about 34% of the distribution, we can just add those two values to find the total area. Remember, area equals probability. So the percentage of scores with a z-value of 1 or less would be 0.5 plus 0.3413. And that's easy enough for me to do just in my head. I can see 0.8413. And if I were to transform that into a percentage, I can just move that decimal place 2 places to the right. So my final answer would be 84.13%. Remember, all of these areas that we see in here, all of these values that are already pre-printed, we can just find them in the table. We already looked at the table and we found some of these values. Here we're just trying to get some practice understanding it conceptually, looking at it graphically. What percentage of scores have a z-value of -1 or less? You're going to see on that z-table there are no negative values. And the reason why the table lists no negative values is because they're really not needed. We can find an area, like the percentage of scores that have a value of -1, which would be right here, or less. We can find that area by looking at its associated area on the right side of the distribution. And that's because a normal distribution and a standard normal distribution that we're looking at right here is symmetrical. So the amount of area on one side of the distribution is exactly equal to the area on the other side of the distribution based on corresponding values. A value of -1 corresponds with a value of 1. So if I want to figure out the percentage of scores that have a z-value of -1 or less, I can look at this area right here that shows the amount of area associated with z-scores of 1 or more. So we're not going to see negative values in our z-table. They're just kind of redundant. So we need to understand that those areas are equal. So in this case, the amount of area would be 0.1587, which is 15.87%. This last one is probably the most challenging, but I think we can figure it out pretty easily based on the segments that have already been labeled for us. What percentage of scores have a z-value between -1 and 1? Now, first of all, I think it's always helpful to mark up the distribution so that visually we can see what's going on. I'm trying to figure out the percentage of scores that have a z-value between -1 and 1. So I'm going to draw a line right here at -1. I'll darken in this line at 1. I'm trying to find this area here in the middle. Remember, if I find the area, I can figure out probability. If I find the area, I can figure out the percentage of scores between those two z-values. Well, one thing that we see labeled that's really very helpful is this information right here. That z-table will tell me how much area there is from the mean to a z-score. And in this case, the amount of area from the mean to a z-score of 1 is about 34%. Well, that shows me half of what I'm trying to find. But remember, the other half of what I'm trying to find is the amount of area from a z-score of 0 to a z-score of -1. That's the exact same amount of area. So this value right here also applies to this section right here. So the percentage of scores that have a z-value between -1 and 1 is just 0.3413 times 2. So let's take 0.3413 and simply multiply it by 2. That equals 0.6826, which is 68.26%. So our final answer is 68.26%. And you might recall that value from what we learned about the empirical rule. About 68% of all scores fall within one standard deviation above the mean and one standard deviation below the mean. I hope this exercise gave you not only a little bit of an introduction into how we're going to use those z-scores in that standard normal distribution, but also just a little bit of information about this table. We're going to be using this table quite a bit as we move along, but before we jump into that table more deeply, let's make sure we understand how to transform raw scores, like IQ scores. Those are the X scores. Let's make sure we know how to transform those raw scores into z-scores. We'll continue to use IQ scores as our example, and we're going to replicate these analyses right here. Let's do those together. As I mentioned, we'll continue to use IQ scores as our example. We know the mean is 100, the standard deviation is 16. We need to transform these IQ scores into z-scores. Here is the formula that we will use. It's very straightforward. We'll just take that raw IQ score, that's the X value, see how far that score is from the mean, and then divide that distance by the standard deviation. So again, the z-value will tell us how far is the score from the mean in standard deviation units. Look at 132. 132 is clearly above the mean, so we know that we're going to find a positive z-score. Furthermore, 132 is a pretty high IQ score. So we should find a z-score that's relatively large. And z-scores get large real fast. A z-score of like 2 and above is starting to get pretty large. Because remember, within 2 standard deviations, 95% of all scores fall. Once we find z-scores above 2, we're talking about some of those rare scores that are way out there on the tails of the distribution. So let's plug things in. X is our IQ score of 132. We're going to subtract the population mean, which we know is an IQ score of 100. And then we're going to divide by the population standard deviation, sigma, which is 16. That leaves us with 32 divided by 16, which gives us a z-score of 2. How do we interpret that? We would say that an IQ score of 132 is 2 standard deviations above the mean. And then when we need to, we can just use our z-table to answer all kinds of questions about the probability of scoring that high. We're going to link these z-scores with probability in the next video. And you're going to see, it's like magic. We make something that's really difficult really easy using that z-table. All right, so we have that one done. Let's look at this next one. An IQ score of 65. 65 is clearly less than 100, so we should end up with a z-score that is negative. And 65 is a pretty low IQ. So we should end up with a pretty large negative number. And remember, at least in my mind, z-scores are starting to get pretty large once they pass up a value of 2 or negative 2. So I always think it's smart to kind of predict what you're going to find before you compute it, because if your answer is consistent with what you predicted, you're probably thinking about it correctly. You're probably computing it correctly. So let's take that raw IQ score of 65. Let's subtract the population mean of 100, and then we'll divide by the standard deviation, which equals 16. Let's just simplify and solve that. 65 minus 100 is negative 35. We need to divide that by 16. That's not something I can do in my head, so let's pull out our calculator. I'm going to key in 35. I'm going to make it negative. And then I'm going to divide that by 16. That equals negative 2.19. Negative 2.19. So how do we interpret that? An IQ score of 65 is 2.19 standard deviations below the mean. Relatively speaking, that's a pretty low IQ. Let's look at this last one. An IQ score of 185. You already know that's like off the charts. An IQ score of 185 is incredibly high. We know we're going to get a large positive z-value. Let's figure it out. So the raw score, the x score is 185. We'll take 185. We're going to see how far is that score from the mean of 100. And then we're going to divide by the standard deviation, which is 16. So in our numerator, we're left with a value of 85. In our denominator, we have 16. Let's just crunch that out. 85 divided by 16 gives us a z-score of 5.31. 5.31. Anytime we compute something, we want to make sure we can interpret it. So let's interpret it. An IQ score of 185 is 5.31 standard deviations above the mean. That is huge. You already know, according to the empirical rule, that 99.7% of all IQ scores are within 3 standard deviations above and below the mean. Now here we're talking about an IQ score that is more than 5 standard deviations above the mean. Just look at this graphic right here. It shows a standard normal distribution. Here's a z-score of 0, 1, 2, 3, 4, 5. Do you see how it's essentially off the charts? The tail of this distribution goes on forever, but it gets really, really, really close to that number line. In other words, there are very, very few people who score in that range. So is it likely that just by chance we would randomly select somebody who has an IQ score of 185 or more? No, it'd be incredibly unlikely. And we can figure that out by using z-scores and our z-table. All right, so now we should be pretty good at taking raw scores and transforming them into z-scores. There's one more thing I want to cover in this video. If we are going to understand z-scores inside and out, forward and backward, we should understand how to transform z-scores back to raw scores. Let's do that next. The good news is that we can easily transform z-scores back to raw scores because we'll just use another simple formula. If I take that formula for z and I just rework it algebraically to solve for x, it'll look like this formula right here. So if I already know a z value, I can transform it into a raw score, an x value, as long as I know the mean and the standard deviation for that distribution. Of course, you'll see exactly what I mean in a minute. We're going to replicate these analyses right here. Let's do that together. Let's change the views. This is the formula that we're paying attention to right here. This first question asks us if a z-score equals negative 1.75. So it's 1.75 standard deviations below the mean. What is the raw score? So what IQ score is 1.75 standard deviations below the mean? Let's figure that out. We'll use our formula. X, which is that raw score, will equal the population mean, which is 100, plus, now I write this in a specific way because the z-score that's coming next could be positive, could be negative, and I don't want that to be confused with that plus sign that I just put in there. So I always put the z-score in parentheses, just to kind of keep it clean, keep it to itself. So in this case, I have 100 plus negative 1.75 multiplied by 16, the standard deviation. All right, let's figure out the multiplication in there. So in our next step, we would have 100 plus, let's figure out what's negative 1.75 times 16. I'm going to key in 1.75, I'm going to make it negative, and then I'm going to multiply that by 16. That equals negative 28. So we're left with 100 plus negative 28. And you probably recall from basic math that 100 plus negative 28 is equivalent to 100 minus 28. Now, we should have predicted earlier that if we're dealing with a negative z-score, negative 1.75, we're predicting an answer, a raw IQ score, that's quite a bit less than 100. And that's what we're going to find. 100 minus 28 would equal 72. So a z-score of negative 1.75 is equivalent to an IQ score of 72. Take a look at this next one. If z equals 0, what is the raw score? Now we should already just intuitively understand what that answer is. A z-score of 0 is a raw score equal to the mean. We know the mean IQ score is 100. Let's just use our formula to make sure that we can find that same answer. We know that x equals mu, which is 100, plus our z-score, which is 0, multiplied by our standard deviation, which is 16. 0 times 16 is going to cancel out, right? So what are we left with? 100. So as we predicted, a z-score of 0 is equivalent to an IQ score of 100. And let's wrap things up by looking at this last example. If z equals 2.05, what is the raw score? We're talking about a raw score that's a little bit more than 2 standard deviations above the mean. Some of this we can just estimate in our heads. If one standard deviation is 16 points, 2 standard deviations is 32 points. So we're talking about a raw score that's somewhere around 132. Do you see how I'm estimating what the answer is going to be? I should find some value that's pretty close to 132. Let's figure out exactly what it is. So x, our raw score, equals 100 plus that z-score, which I'll put in parentheses, 2.05, multiplied by our standard deviation, which is 16. So I'm left with 100 plus, let's figure out what 2.05 times 16 is. I'm going to key in 2.05 and multiply that by 16. That equals 32.8. So I'm left with 100 plus 32.8, which of course equals 132.8. And that's right on track with what I predicted. So I'm probably thinking about it right. I'm probably computing it right. I'm probably on the right track. I know my handwriting can be atrocious, so you have this right here so that you can check your own work. I think that's enough for now, my friends. In our next video, we're going to link these z-scores with probabilities. In other words, we will link these z-scores with our z-table so that we can answer questions about area, because area will tell us directly about probability. I'll see you in that next video. In the meantime, be safe.